Okay, I am recording now though. So again, two functions that are important to business applications that we haven't looked at yet as far as taking the derivative goes. So we are going to look at exponential and logarithmic functions. You guys, the set of exponential and logarithmic functions is very large. We definitely get to narrow it down, and I'll show you how we do that, starting with the exponential. So it might have been a while since you have even looked at an exponential function, but it's called an exponential function because x is in the exponent. So for example, my children, they like bang the markers against the wall or something. I don't know. It's a problem. And I tell them to lay off my black markers. I'm like, hey, don't touch the black markers. But then I think that just makes them want to touch the black markers more. So they've got to them all. We'll try purple. That's a pretty good one. Okay. So you guys, for example, y equals 2 to the x is an exponential function because x is in the exponent. Y equals 1/2 to the x. Another example, there's x in the exponent. It doesn't have to just be x. We might see something like y equals 3 to the 2x plus 5. This is an exponential function because it has the variable in the exponent. So these are just some examples, but honestly, guys, these three examples, these aren't functions we're going to take the derivative of. We're only going to take the derivative of one type of exponential function. While these are all exponential, notice the base. So the base is the number that you raise to an exponent. 3, 2, 1/2, it's changing, right? But the fact that x is in the top exponent is not changing. So let me show you the exponential function we are going to take the derivative of. While these are great examples, we don't have the time to cover how to take the derivative of all exponential functions. We are going to take the derivative of what we usually call the exponential function, the important one. You guys, the one that has tons of application, especially in financial realms. We're going to look at e to the x. You guys, a special case of the exponential function where your base is e, and you raise it to the x power. You guys, a little background on e, if you don't remember, it's like pi. It's actually a constant value. It is not a variable. We call it e, remember, because it's an irrational number. So it's the easiest way to just give it a letter and call it that all the time. So we call it e. A lot of times you might hear e being referenced as the natural number. A lot of people call it that. It has a lot of applications, not just financially, but anytime you're trying to describe natural growth, like bacteria population growth, if you're in like a scientific realm. Business, you guys, when we want to talk about natural growth, usually we're talking about compound interest. You know, you put money in the bank and it grows continuously on a continuously compounded interest. That formula can't work without e. So natural number, we use it a lot. It's the one we're going to use, and we need to know how to take the derivative of it. Okay, so if this is where we're starting, I want to take the derivative, and I don't know why I wrote it over here, and then I don't know, guys. Okay, so here's the deal. This is probably the easiest derivative you'll ever take in your life. Its end result is the easiest. What is very hard to show, especially in this particular class, like if we were in just a normal calc class, we would take the time and we would write a proof. We would put this into our definition of the derivative, you know, with the limit and the f of x plus h minus f. We would do all that. And we would do a lot of work, a lot of complicated math to get down to our answer. But it would confirm and it would prove that it's the case. But you guys, we don't, for one, just time constraints. And for two, it really is outside the scope of this particular class, which is more applications based for, you know, business applications. So I'm going to give it to you and you're going to trust me. And if you don't trust me, you can always look it up. But you guys, if you start with y equals e to the x, and you want to take the derivative of e to the x is itself. You guys, we put it into that definition and we do a bunch of lines of work. And at some point we get down to this. And think about how frustrating that must have been the first time. But anyway, you guys, e to the x, you take the derivative, it is the same exact thing. There's no tricks here going on, guys. If I say, hey, what's the derivative of e to the x? You're going to tell me, oh, it's e to the x. It's itself. So you guys, it can't really get much easier than that, right? No, it can't. It can get a little bit harder. You guys, let me give you an example. I'm going to use function notation this time. So here's a question. It's not always just an x in the exponent, right? Like I had one over here and it had like multiple terms in the exponent. That can happen with e too. You guys, I might have something like f of x equals e to the 3x. That's a little different, right? The same rule, if you have e to the anything, this derivative rule applies. It's going to come down exactly as is. But what's that rule that we use when we say, ooh, but it's not just an x? You guys, I hope we're thinking about chain rule. Remember, we had, you know, we had something taken to a power, and I did the power rule around it like this was just an x, right? But then what did I say? I said, oh, but it's not just an x. What did I have to do? I had to use the chain rule and I had to tack something on the end, right? We should be really good at chain rule by now, but you guys, chain rule doesn't stop with the power rule. You guys, chain rule can apply to any type of function there is. So it has to apply to this kind too. So think about what we do when we use the chain rule. We think, okay, there's really like two functions going on here. There's a big picture, like what's happening on the outside. For us in the last chapter, the big picture was the power rule, right, around that term. And then we focused on what was inside. We took the derivative of that and we stuck it on the end. Same type thing happening here. There's a big picture and then there's something on the inside we have to deal with. So, you guys, your big picture, if you have an e function, if you're looking at an exponential function, the outside function, the big picture function, whatever you want to call it, is always the e to the thing. You guys, and you guys, because it's e raised to a power, taking the derivative of that big picture function means that this term comes down exactly as is. That's me taking that first step derivative in the chain rule. So I say, okay, I have e to the 3x. First step, take the derivative of it as an exponential function. I bring this down exactly as is. Nothing changes. And I say, oh, I did it. I took the derivative because that's how it works, right? It just comes down the same. Yeah, kind of, but this isn't just an x. This wasn't just e to the x. It's e to the 3x. So after you bring down your exponential term as is, all I have to do is take the derivative of what is here. You guys take the derivative of 3x. That's 3, right? Chain rule works the same. You still just stick it onto the end with multiplication. So what I end up with, and usually guys will put the number in front of the e term. So I'm going to call this 3e to the 3x. So this is how the chain rule is working with an exponential. The first thing you do is use your exponential rule, which says this comes down exactly the same. Second thing you do is you look up in your exponent and you take the derivative of that exponent and then stick it on the back. And you do that same thing every time. So let's do it again. So if I have f of x equals e to the 2x squared. Okay, so I look at this and I say, hey, it's exponential, but I also have to consider what's up here at the end. That's the chain rule part. So my first step, always, guys, your first step, take this e term, bring it down exactly the same. Nothing changes here. I'm going to have the whole e to the 2x squared. Now, what's my second step? I take the derivative of that exponent. So the derivative of 2x squared, you guys, that's going to be 4x. And I stick it on the end. And that's it. And you guys, I usually like to put the x terms in front of the e's too. You can write it like this. That's totally fine. I would write it as 4x e to the 2x squared. But either way, that's saying the same thing. So here's the exponential part. This is what we got from the chain rule. What about this one? So let's mix and match. You guys, let's look at a function that has a lot of different things going on. Sorry. Let's say I've got y equals 3x cubed plus 4x squared minus e to the x cubed plus 2 plus 7x. Is that too far? Let's take off the plus 7x because my head's just going to cover it. So let's just leave it here at the plus e to the x cubed plus 2. So this function has multiple types of terms, right? We have the normal polynomial terms where it's just x raised to a power. I know how to deal with that. We also have the exponential. Remember, you get to do each one separately. Each of these terms you're going to use, you know, the rule that applies to that. Just because it has an exponential term in the function doesn't mean that you have to do some crazy exponential rule on the whole thing. So we can still go term by term, and we use whatever rule we need to use for each one. So let's get started. You guys, these first two terms should be really easy for us at this point. You guys, let's do this. We get 9x squared plus 8x. So you guys, you'll notice that from this point on, when I use the power rule, you know, sometimes I would do extra steps and I'd put the 3 times 3 and then the 4 times. I'm not going to do that anymore. We should be faster at that and more efficient at the power rule to be able to just do it in one clean sweep. So we get 9x squared plus 8x minus, and then we deal with our e term. So first step, it's exponential. Bring it down exactly as is. E to the x cubed plus 2. What's my second step? You guys, take the derivative of this exponent. So you guys, the derivative of x cubed plus 2, well, that's just 3x squared. So your final answer for this function, we've got the 9x squared plus 8x minus, you guys, if you want, you could put this 3x squared in front of the e term. That's what I would do. I would call this minus 3x squared times e to the x cubed plus 2. So just whatever rule you need to use, you can use it at any time. It's not a one size fits all, even in the same function. So you guys, we'll go back and we'll do some more exponential problems, but right now, I want to talk about the logarithmic side of today. So, logarithmic functions. Let's do some review. You guys, if you don't remember tons about logarithmic functions, that's okay, because we're not going to be working with them in depth. What we're going to be doing is just taking derivatives of them. So, you guys, logs. There's a lot of different types of logarithmic functions. So there's, remember, if you don't, that's okay, but logarithmic functions always have bases. So you might see log base 10, or log base 2, or log base whatever, but you always have that base. and that's what changes a log function from one to another. But you guys, we only care about one base, and it's the same base we care about in the exponential functions, guys. The only log I care about in this class is log base e. Now, you can see how I wrote it here, and if you don't remember log notation, usually it starts with an log, and then we have this little subscript, and that's what says what your base is. You guys, so this does say log base e, but that is not how we write log base e. It's not even what we call log base e. Because log base e is very important, it's a very special case of logarithmic function. It has its own abbreviation and its own name. So instead of saying all this, we just say ln. Notice we don't have to say a base because just the ln part tells us the base is e. We call it the natural log. So the log function we're going to take derivatives of is natural log, and it's going to be notated just like this. You're going to see ln, you know, oh, that's the natural log. Okay, so that's just, you know, a little refresher. So when I write that ln there, you guys aren't just like, wait, what, you know, what is happening? They're not variables L and N, right? This is the function statement. So natural log is the function we're working with. Here's what it looks like in a function or an equation. This is the function we're going to take the derivative of. Y equals the natural log of x. So you guys, when you have a natural log statement, it's never by itself. This doesn't make sense. You have to have this spot here for your input. So natural log x means that you're going to put x into the natural log function. So this is our function where x is going into the natural log function. That's what this says. And I want to take the derivative of this natural log of x function. Okay, so natural log's not as easy as e. It doesn't just stay exactly the same, but it's not that bad either, guys. So you have the natural log of x. When you take the derivative, what happens is you get 1 over x. And that's it. You guys, I want you to think about x as a placeholder because we know it's not always just an x here. In another way of saying this, why don't you say, I've got the natural log of something. And when I want to take the derivative, I know I'm going to get 1 over that something because it can be anything there. Now, if it's not just x, we know there's probably some chain rule going on, and we'll definitely look at that. But the thing that's happening, the thing I want you to see, the real rule here is that whatever your input is for your natural log, whatever you're trying to put into natural log, when you take the derivative, all that happens is it gets a 1 over that thing. So let's look at an example. Now, this is the most straightforward example when we just have x. But we can look at examples where we have to use some chain rule, you know. So you guys, let's look at this one. What if I have y equals the natural log of 2x plus 3? So now you can see it's not just an x here. I say, okay, I'm taking the natural log of this. When I take the derivative, because the main thing happening here, the big picture, the outside function is natural log. I know the first thing I'm going to do is I'm going to take this and I'm going to do 1 over that because that's how you take the derivative of natural log. That's the rule. So y equals natural log of this. My derivative looks like 1 over this. But, you know, of course, this is not just an x. Because it's not just an x, what do you think I'm going to do with that? I'm going to find its derivative, and I'm going to multiply it by this. So you guys, what's the derivative of 2x plus 3? Isn't that just 2? So you're just going to have a times 2, but you have to be careful about where you put this 2. This is not a 2 on the bottom, right? This is a 2 on the top. This is 2 over 1. So when you multiply by the derivative, when you get this link on your chain, it can always just sit up here. And that's the way we like to see it. So I could write this as 2 over 2x plus 3. And then this is my derivative. Yes, I used the natural log rule and I used the chain rule because this wasn't just x. See guys, that chain rule, we get really complacent with it, like in those first few sections, and say the only time we ever need this is when we have some x term raised to a power. Not the case, guys. The chain rule applies in every function, every type of function. Whenever it is needed, it applies. But what's nice about it is it doesn't change. You guys, even though the big function, like the outside function, is changing, even though this is now natural log instead of just some basic power rule, once you do the rule for this outside function, remember your chain rule is always the same. It's always take the derivative of the inside and stick it on the end. Every time you do that same thing. Let's do another one. Let's do y equals the natural log of 4x squared plus 2x. Okay, so I'm going to do this. So the first thing I'm going to do is say, oh, hey, this is a natural log function. I'm going to take the derivative as it's a natural log. So if you're taking the natural log of this, when you take the derivative, what you're going to get is 1 over all of this. Notice from here to here, just like from here to here, those terms do not change. Then that's basic chain rule, right? When you bring that first step down, this never changes. What you do is after you do the natural log rule, you say, hey, but I do need to take the derivative, whichever one you want to look at, because they're the same. I do have to take the derivative of this, and I'm going to stick it on the end. So let's do that. You guys, this is going to have multiple terms in the derivative, so you do need to parentheses it, group it. You guys, but the derivative here is going to be 8x plus 2. So what do I do with that? Remember, this is multiplied. It's not on the bottom of a fraction. It goes on top. So you can absolutely write this as 8x plus 2 over 4x squared plus 2x. Sometimes these fractions can be simplified. Sometimes they can't, and sometimes they can. I would not simplify at all because when it comes to canceling stuff out of tops and bottoms of fractions, especially when you've got x's involved, there's a lot of margin for error because you want to cancel things that really don't cancel. Like in this example, the only thing we could take out of these terms is a 2. That's the only thing they all have in common. But I'm not going to worry about it. I'm going to put my answer in like this and leave it that way. I'm saying that because MATLAB might simplify some answers, so you might see an answer that doesn't look like yours. And like we saw on the homework from 11.7, it's like the way they write their answers sometimes is just like so overcomplicated. And you're like, why? You know, how did they get that? Well, just remember, they've done a lot of extra work after they actually got their answer that's not necessarily required. You know, this is where I would leave this here. Okay, so here's what I want to do. You guys, I want to do one more problem. And yes, it's kind of a shorter day. I want to do a problem that involves logs, exponential, chain rule, and product rule. You guys, I want to put this all together because that's what we're going to be doing. And obviously it'll have power rule in it, right? Because everything does. But I want to put it all together. And I'm going to take up the whole board. So I'll make sure you guys have this all written down. But guys, what I want you to get out of this is even though we're done with chapter 11 at this point, even though you've tested over most of chapter 11, those basics, you know, those rules that we learned, we never stop using them. So even though we're learning new rules, you know, some math is like that. Like you do one thing and then in the next unit or section, it's totally different stuff. and you don't even use what you used before. That is not the case, guys. Chapter 12 is just applications of what we just did in chapter 11. We're gonna have to remember it all. And we're gonna be carrying this stuff throughout the semester, so you really want a good grasp on it. Here's my problem. I have f of x equals e to the 3x squared times the natural log of 5x cubed plus 2x squared. Okay, let's stop and assess. So first of all, you can see exponential, you can see natural log. You're like, oh, okay, I'm just going to use my new rules from 11.8. Awesome. What else do you see? I see a lot of chain rule in here. This isn't just natural log x, right? This is natural log of all of this crap. So I'm going to have chain rule. Same here. This isn't just e to the x. I'm going to have a chain rule up here. But what else am I going to have? You guys, these are multiplied together. Unless you can actually multiply these together in some functional way, you have to use product rule, guys. These are not like terms. And yes, multiplication is very fluid and you can multiply a lot of different things together. Putting these together, multiplying wise, is only just writing them next to each other. You can't actually functionally get a new answer out of this. You can't combine them because they're so different. So because I have two products that I cannot multiply together, I can't combine those, I know this is product rule. Term with an x in it times another term with x's in it. So label, you can call this u, e to the 3x squared. V is going to be your natural log statement. So anytime you have now if these were plus, you would just do them separately, right? But it's not plus, guys, it's multiply. Anytime you have an e times a natural log statement, that's going to be a product rule situation. Okay, so let's go over this side and find all our derivatives. So if u is e to the 3x squared, then the derivative of u, remember how this works, this e term comes down exactly the same. So you're going to have e to the 3x squared, but then you're going to have to multiply by the derivative of that exponent. So the derivative of 3x squared is 6x. So you're going to end up with 6x e to the 3x squared. This is du. That's the derivative of u. Let's do the v's, you guys. So v is this natural log of 5x cubed plus 2x squared. Let me erase that u and v here. So let's find the derivative of v. So remember, you have the natural log of something. You want to take the derivative, it becomes 1 over that thing. So I have 1 over 5x cubed plus 2x squared. Remember, that stays exactly the same. And then chain rule. Take the derivative of this. So I'm going to tack on to the end the derivative of all this, which is 15x squared plus 4x. Remember, you don't have to leave it like this. You can take this and you can put it on top. So let's do that. So on top, I'm going to have 15x squared plus 4x over 5x. I don't really need parentheses here. I don't know why I did that. Remember, if you have a fraction bar groups also. 5x cubed plus 2x squared. Too many parentheses is never a problem though, so. Okay, so this is the derivative of v. I'm gonna have to erase some so I have room for stuff, but this is du, this is dv, and we already have u and v, and I now need to put them together as product rule, right? That's gonna be a lot. If I just erase a little bit there, I should have enough room. Okay, so finding the derivative of f of x. It's u times the derivative of v. So let's start there. u is e to the 3x squared times all of this, derivative of v, times 15x squared plus 4x over 5x cubed plus 2x squared. This looks ugly, but I'm just going to leave it as is, guys. This is u times v plus v. V is just natural log 5x cubed plus 2x squared. Now, I don't have room, guys. You probably have room. So pretend this is all on the same line. This is v, and now I need to multiply that by the derivative of u, which was the 6x e to the 3x squared. And you guys, there is not anything I would do with that. I would write it as is. Remember on the chain rule problem that was chain and product put together, and MathLab does this crazy answer, but I told you to leave it, like once you put it in the product rule order, just leave it there. It's gonna take it, same thing here. You guys leave it here. U, dv, v, du, just leave it like that, put it in. Things you'll need to be careful about is make sure when you do a natural log that you do have parentheses around the whole thing. But other than that, that's the main thing you have to be careful about. Guys, parentheses, if they weren't here, it means you'd be taking the natural log of this first term, but not the second term. So keep that in mind. Your whole input is going to be with parentheses, and you need to keep it that way. So you guys, I realize that this seems like a lot, and it is a lot. But you're going to have a lot of practice. You're going to see your homework coming up probably after my next class, after you guys, then I'll be getting up and putting up homework and stuff for this stuff. You're going to see a lot of practice because that's what's going to be needed here. But we're going to get it. You're going to practice it and you're going to get it, and it's going to make you stronger, right? After all this stuff, you're going to have tons more practice on power rule, on chain rule. It's all just going to make you more fluent in derivatives, and that's the goal. But yeah, so next time we are going to move on to chapter 12. Definitely look for homework later in today for this stuff so you can get started on it. And again, if you haven't turned in your paperwork for your exam, that needs to be your first priority. Get it into me, D2L or email, I don't care. D2L is probably easier for everybody, but if you can't get it on there, email it to me. But I need it, or you're going to be very sad about your test grade, okay? So get that in, and I will see you on Wednesday.